Introduction. I'm Chaitanya, and today's discussion is going to be on microcontrollers and microprocessors. Okay. Woo! Thank you. One person that appreciates that. So, you all have been using the Arduinos, the Raspberry Pis, the Aferos for some, and also, what else have you been using to code stuff onto your chips? Anything else? I said the Pi, I said the Arduino. Anything else? The Beetalino. Where's Sneha? Yeah, there you go. So all these things, and then you have your computers, which are actually huge things, bigger than what the Arduino board looks like. So to start off, a microcontroller, I'm gonna draw an empty box. What do you think it's comprised of? Does anyone know?
You said it's empty. So
I'm gonna start with an empty box and fill it with stuff that you tell me. So it's the brain of your circuit, right? So what is the brain of your personal computer? What do you call it? CPU. That's right. So yeah, thank you, Raymond. So it should have a CPU to process things. So as to store the code that you put onto it, what? Sorry? Flash, which is a type of memory. Very good, Andrew. Okay. What else? You make connections. That's a part of the software. I'll consider that to be a part of the memory. If you want, so okay, let's make two parts of the memory. One which stays permanent, which we can say is the ROM, and one which is erased after you turn off the microcontroller, which we can say is the RAM. Does anyone know what it stands for?
RAM, access memory.
Okay, and what about the ROM?
Very dull.
Okay, great. Did everyone hear that?
No.
So this is the random access memory, which clears itself after you turn off the microcontroller or the microprocessor. It works the same both ways. And the read-only memory stays even after you turn it off. So, can anyone tell me what their uses might be? Silence. Okay. Like he said, bootloader. The bootloader is a part of software that you need to turn on your microcontroller or microprocessor, which should be there every time you turn it on. So where do you think can you store it? The RAM or the ROM?
ROM.
The ROM, that's right. And what about stuff like variables, which are only generated when your code runs? Where should they be stored?
RAM.
Great. What else do you see on your microcontroller that is not there in the box right now? Brian?
It needs some way to communicate with like the external circuit.
Okay. So what do you see on your board that communicates with the external circuit?
Well, as a USART.
Okay. That's a communication protocol. That's nice. Let's add a USART here. Brian, can you tell me what a USART stands for?
I don't remember what the acronym stands
Okay.
for.
It stands for asynchronous, synchronous, I don't know.
Universal.
I know RT is
Yeah.
receiver transmitter.
Oh yeah.
Universal synchronous / asynchronous receiver / transmitter.
Fancy stuff.
I mean, I don't know why we can't all just remember that all the time.
Fancy stuff. Yeah, it's much easier to say UART and USART. But yeah, that's a communication interface. What else? Don't you see pins on your board that you put wires onto? Yeah, so what do those pins indicate? What do they take in? They take in electrical signals, right?
Yeah.
Sometimes input and sometimes output. So can I say I/O?
Yes.
Okay. And all of this is on one chip, right? So when all of these things are on one chip, it's called as a microcontroller. And the uses of a microcontroller are generally for a specific task, in which case you know the relation between the input and the output. You know that if you apply this input, you're going to get output in this range, something like that. It's fairly easy to understand what the input will be and what the output will be. But in case of a microprocessor, the only thing the microprocessor has on the chip is the CPU. That's the biggest difference between the two. So can you tell me something about the cost of these two? You've got everything on one chip here and just the CPU here. But keep one thing in mind. In this one space, you've got just the CPU. So imagine how much more computational power it will have. So which one do you think will be costlier? Tell me.
The CPU on the right,
And why do you say so?
because it has more processing power.
That's right. The more the power, the more the cost, and that is why it's used in your computers. And your Arduino is not able to power your computer. That's the reason why. Because these things are fixed for a microcontroller. You cannot change the number of pins on it unless they've given you headers. You cannot change the processing power. You cannot change the amount of memory. And also no communication protocols. You cannot add more stuff unless you use the pins to add another peripheral to it. But for the CPU, it's an open world. You can connect as much RAM as you want. You can connect as many peripherals as you want, and also have anything like a USB port, or if you want, a satellite. So what do you think is the use of both of these in day-to-day lives? For smaller applications, say you want to control an LED or you want to control a switch in your house, what will you use? Okay. So for smaller applications, you'll use a microcontroller, where you know what, it's a singular application. Probably for two or three applications you can use a microcontroller because of its limited computational power. But then what about complex things like running your systems, running, what do you think do supercomputers have in them? A microprocessor or a microcontroller?
Microprocessor.
Okay, that's right. And again, I'll throw a term at you. Internet of Things. Do you know what it is? No? Can someone wait?
Kind of like everything is, say, as an example, like in your house, your TV, your refrigerator, your air conditioning system, they're all connected to each other.
Okay.
Say like you open up your door, then your AC turns on because it's registered that you opened the door and came into the house.
For that kind of system, what machine will you use? A microprocessor or a microcontroller?
Microprocessor.
Okay, but what if I say that each of your fridge, your AC and your lights have different systems? Do you have a microprocessor in all of them? Or will it be easier to have a microcontroller embedded in each one of them?
Maybe a microcontroller in each one and
Who thinks it's a microcontroller? Okay.
I have a question.
Yeah, sure.
In that example, isn't it kind of a distributed systems type thing? Because each of your appliances, your refrigerator, your air conditioning should be feeding like information to one kind of head processor that then handles all the controls of, oh, the door is open, that feeds information, and
Okay.
oh, turn on the AC.
Let me give you an example. Say you're trying to. Okay. Say you're trying to communicate one phone that has Bluetooth, only Bluetooth, nothing else. A phone that has only Bluetooth connectivity with another phone that has Bluetooth connectivity. Do you need a central processor to tell that what data you're supposed to pass, or they can communicate directly with each other?
They can communicate directly.
So replace Bluetooth by the internet. That's what IoT is. Your devices having a microcontroller of their own, and they communicating with each other, and only for specific functions. So now who thinks it's a microcontroller? Still no one? Okay, I see some hands. Who thinks it's a microprocessor? Okay.
I have a question.
Yeah, sure.
So what if I wanted to change the function or the relation between the different Internet of Thing pieces in my house? So what if I wanted to now turn the heat on when I open the door instead of the air conditioning, or turn the lights on when I open the fridge or something? Like if I wanted to make a change.
Good point. So the only thing you're restricted by is the amount of memory and the computational power. You can keep adding more functions as long as the CPU can handle it. And in those terms, I think a microcontroller would be more appropriate when it comes to IoT. The world is going towards that. For example, who knows about the Intel Edison? What is it, Andrew? Board. Okay. Is it a microcontroller or a microprocessor?
I don't know.
It's a microcontroller. Anyways. So yeah, in terms of IoT, your devices need a specific chip with everything embedded on it, and it should be able to do stuff.
Couldn't you use a Raspberry Pi as a part of Internet of Things device?
Okay, thank you for bringing that up. Back in the day when the Raspberry Pi was not there, these were the only categories that existed: the microcontroller and the microprocessor. By the introduction of the Raspberry Pi, they introduced something called as a microcomputer. The Raspberry Pi made a classification for itself. It's everything on this chip, but with more power, and instead of the controller, it becomes a computer. That means it has a software that you can use to program it and like do stuff with it. For example, the Arduino uses its IDE, and you can put in raw code, and you cannot run any applications on it. That's the difference between a microcontroller and a microcomputer. And also the Raspberry Pi has its own operating system that it runs on. You can run applications on it. You can run Python IDE. You can run lots of stuff, I presume. So yeah. So by the introduction of the microcomputer, it has become challenging whether to use a microcontroller or a microcomputer, but the question still remains on how much processing power you need for that, for whatever you have to do. And so yeah, so can someone tell me any other microcontroller types other than the Arduino and other than the Arduino? Does anyone know of any? I just now said the Intel Edison. No one? Okay. Yeah?
A Node MCU.
Okay. Is anyone using the Node MCU? Someone
Couple
try?
people. I see one hand back there.
Okay, yeah. Some people try it, some people burn them, some people do stuff with it, yeah. Some people succeed. But yeah, the Node MCU is one, the STM32 is another, a Pharaoh apparently is another, which is a new one, which I didn't know of.
The what?
And a Pharaoh,
A pharaoh?
yeah.
How do you spell that?
She has one. Yeah. AFERO. And the Betalino for Sneha, who's using it for doing health stuff. Yeah.
So is the Arduino is Arduino a microcontroller?
Uh-huh. Okay. Can you justify?
So what's on your Arduino? There's a chip, right?
Mhm.
That chip is the microcontroller.
Oh.
But the chip isn't an Arduino.
Oh, okay.
The
So
chip
you
is
mean
not
the-
Mega
okay.
328 on an Arduino Uno.
Mm. Good point. So, so the Arduino is essentially the platform that they've created for you, and the chip on that board is the microcontroller, which has all the things embedded. Oh, we're missing one part, by the way. Yeah, tell me.
So the name of what an Arduino is, it's called a development board.
Okay,
Yeah.
great. Thank you for that. So we're missing one thing here, and does anyone know what that is? Has anyone heard of a clock that goes inside? Yeah. Yeah. So it's a timer. It basically helps you to keep track of the time when things are running. Has anyone wondered how your computer is able to tell you the exact time every time you switch it on? even though you turn it off beforehand. Ben?
For most laptops, doesn't it communicate with the internet and get like
Even if
the
Wi-Fi is
international
off, it
time?
will still tell you the time.
I know at least I have one student. Who else is using a real-time clock?
Yeah, right.
Somebody want to tell, somebody who's using a real-time clock, want to tell what it does?
Yeah. Ritik?
Real-time clock is like where it like counts the seconds to calculate time.
Okay.
But it doesn't apply because you turn it off, right?
Mm-hmm.
What does your real-time clock have in it? Like a knob, what does your real-time clock have on it? So that if you like unplug your board, it still keeps track of time. A battery. So it has its own independent battery. So like all of your computers have a little tiny watch battery
Yeah, the
inside
CMOS
of them
battery, the small ones,
that's independent of your main rechargeable battery.
and that's what keeps track of time for the computer. And yeah, so other than that, yeah, so I told you about the cost, I told you about the memory. Yeah, let's talk about I/O. Yeah, Bart?
So you were talking about microprocessors, but what exactly is a CPU?
Okay, good question. I have to. I can tell you that. That's a high level question. So, as a computer architecture course, as a part of the computer architecture course during my master's program, we had to design a CPU. And I can tell you what parts it actually is made of, at least a simple CPU. There is an ALU to do all your mathematical. So like Ben said yesterday, there are like 5 levels of languages. It starts with level 1 and ends at level 5. Level 5 being artificial intelligence and level 1 being assembly. Assembly is nothing but the most difficult way for human beings to understand what a computer is doing. Below that says binary, which is essentially 1 and 0. So let's just say you get. So what is an ALU? An ALU is nothing but a block that performs operations, mathematical operations, and that is a part of the CPU. Then there's something called as instruction memory, which stores all the instructions the CPU is getting. Then there's something called as a register file, which has all. So the CPU cannot store tons and tons of data. It stores only a part of the data which it's actually working on for that time. That's stored in the register file. Then there's something called as the load memory, which is essentially the external memory, or the RAM. And there's something called as a program counter, which proceeds to the next instruction, which is essentially a clock. It is keeping the time for the CPU. All these things together make the CPU. Okay, so let's talk about I/O. As we said, it's input-output, right? So, can you tell me the fun input and output modules that you were working on? I want examples, as many as I can have.
Like the different types of,
Yeah, the I/O devices that
like you're talking about like analog and digital? Or-
both. What is analog and digital?
So,
Let's throw that.
so digital is like when you only have like 2 options, high or low.
Okay.
Analog is like anything in between. For example, if you have like 0 or 5 volts,
Mhm.
5 volts could be high and 0 volts is low, and that would be digital. But then if you have something in between, you could assign values to it, and it would become analog.
Okay. So, do you know if you're... So, can you convert from one form to the other?
Yeah.
Okay. And doing... So, what is that component called that converts?
PWM.
Those are again digital waves.
But isn't that's used for converting digital to analog, right?
That is, so you give the processor the notion that it is being converted, and you see it as being converted, but it's actually a digital wave that has like 2 values, high or low. PWM is essentially pulse width modulation, for those of you who are not using it, and it's a way of representing a digital wave and like giving different values in terms of analog. So what is analog? Analog is something, so let's take two values. Suppose 0 and 5. It's 0 volts and 5 volts. So a digital system can just take two values, like 5 volts and 0. So this is 0 and this is 1. And analog can actually take values in the middle of it. And that's the difference. For converting this analog into digital, we use pulse width modulation. Consider this as a square wave which has just two values, 1 and 0, 1 being here, 0 being here, and you play with the x-axis right here and you get different values, different on times and different off times, and that indicates the processor that it's a different wave than what it was before, and that's how you get different values using pulse width modulation. It's pulse width modulation. You vary the width of the pulse and you get different values using that. That's how it works. Yeah, so pulse width modulation. Where have you used that part?
For the Arduino.
Okay, but for what component? We're talking about I/O. So, what sensors have you used in your?
Oh, for the servos.
Okay, servos. So motors. Motors one part, which is probably the most common of all. What else? What else? Yeah. Yeah, LEDs is also. Other than that, I want fancy ones. I know you've used a couple of them. Yeah. Great. Camera.
Are you
What
talking about
else?
all I/O or just PWM things?
No, all I.
Okay.
What else can you put? Flex sensors? Yes. What else? Timothy, what have you used?
The diode.
Yeah. I mean, what have you connected to your microcontroller? Where are you? Yeah. What are you using? What are you making?
You mean the diode or
What have you connected on top of your microcontroller?
I don't remember.
It's an NFC sheet. So yeah, NFC is another thing. And what else? Give me some fancy ones. Bits?
I don't know. I only have two things connected, which you've already put on there.
Okay, but what about the others? You keep seeing people doing stuff, right?
Not really.
No? Okay, you use a phone, you use a smartphone. Anjali?
Fire sensor.
Yeah? What else? Buzzer? That's sound. Do you see something that is common in all of these things?
On the board.
What do you get at the output of, like, what does the board get in terms, like, what signals do they deal with? What are the common signals that they deal with? The IR takes in or out IR signals. It takes in IR signals, gives out IR signals probably, let's say. But it takes in or out and converts them to what? The NFC shield, it reads an NFC tag and converts it to what? Electrical signals? Is that common here? They all have something or other to do with the electrical signals?
Yeah.
Yeah, so they either take in electrical signals and convert it to some other form of energy, or they give in electrical, they take in electrical energy, or they give out electrical energy. So such type of devices are called as transducers, which convert one form of energy to another. And when they deal with electrical energy, it's called electrical transducers. I guess that's all that I have. Do you have questions for me? Yep.
So that electrical energy is converted to what then?
It depends on the model. For example, a microphone, it converts sound energy to electrical signals. A speaker, it will convert electrical signals back to sound energy. An LED will convert electrical signals to light. And so on and so forth. Yo,
What's the difference between IM and your RAM counterpart in CPU?
Can you repeat the question?
What's the difference between the IM and the RAM counterpart in the
What
CPU?
is IM?
The instruction memory or something?
Oh, okay. And the difference between the IM and
The RAM counterpart, I didn't see what you labeled. I think it was LM or something.
oh, that was the load memory.
Yeah.
So that's the RAM. So the CPU has a little bit of memory of itself, which is the register file. It's like 32-bit registers, like 32-bit, like literally 32-bit, and these are 32 in number. So that's the only memory the CPU has. You need more memory so as to work on more data, right? So that time the RAM is helpful, which has probably 4 GB. Nowadays even 64 in some of them. And on top of that you have your hard disks, SSD or whatever, 1 terabyte, 2 terabyte. So this is the most accessible memory for the CPU. This is the next most accessible. And then lies this, which is the most difficultly accessible memory for the CPU. Yeah. So every time this needs to be accessed, that part is copied into this, if it can be, and if it's gonna be used regularly. And after that, after it's been used, it's just overwritten by some other part of data.
You want to mention the cache?
Oh yeah. So again, the cache is again
Between the register and the RAM.
yeah, it's between, but it's sometimes on chip, and sometimes it's not.
I'm not aware of any CPUs that don't have on-chip cache.
So the very first ones like.
Well, okay. I'm not aware of any modern CPUs that don't have on-chip
Okay,
cache.
Well, the cache memory is again, after these register files lies the cache memory. So again, something about memory is, the lower it goes, like suppose this is the register file, this is the cache, this is the RAM. The lower it goes, the more expensive it gets. If you want a terabyte of cache, it will be like way more expensive than what you will pay for a terabyte of hard disk space. So yeah, that's
Also,
another
you
thing.
can't buy a terabyte of cache, in case any of you
Oh,
were
there's,
thinking
I
of
mean,
that.
there's no processor designed for that. Yeah. So yeah, I guess that's all for the day. I'm running out of time. So, any questions?